the discovery of fission. So in the mid-1930s, Enrico Fermi attempted to synthesize a new element by bombarding uranium with neutrons. And the idea was, if the neutron got incorporated into the nucleus, it might undergo beta decay and convert a neutron into a proton, and thus you'd have a different element. So this was the idea. So he did detect beta emission, which is what he was expecting, but for whatever reason, he never chemically examined the products to see if a new element had formed or not. Meitner, Strassman, and Hahn repeated his experiments. They found that the products contained several elements that were lighter than uranium. Fermi was expecting something heavier than uranium. They reproduced the experiments, which is very common. You're interested in a general field and you look up other people's research and you're like, well, I want to try that too. And so you try it, and then sometimes we learn new things because of that. So they found that the elements were lighter than uranium, and this was huge. So on January 6, 1939, they reported that the neutron bombardment of uranium resulted in nuclear fission, the splitting of the uranium atom. And this is a picture of Lisa Meitner. So the uranium atom split into barium and krypton, 3 neutrons, and released an enormous amount of energy. So this is uranium-235 that did that. Less than 1% of all uranium is uranium-235. Uranium-238 is the most common isotope. It does not undergo fission, but uranium-235 does. So if you have a sample that is rich in uranium-235, it can undergo a chain reaction. So you bombard one uranium nuclide with a neutron. It breaks into krypton and barium, releases 3 neutrons. Those 3 neutrons can interact with other uranium-235 nuclides and cause the same fission reaction, each of those generating 3 neutrons. And then these neutrons can go on and interact, and this is a chain reaction. It will keep itself going. You start it, and then it will keep itself going. So the fission of one nucleus induces the fission in other nuclei. So you have to have a certain concentration of uranium-235 for this to happen. Because if you only have a few uranium-235 atoms, these neutrons are going to run into uranium-238 instead, and nothing's going to happen. So this is called a critical mass, the amount that's needed for the reaction to be self-sustaining. And so this reaction can be used to make an atomic bomb, because you can see how this could quickly get out of control, right, and literally be explosive. Yes, thank you for your applause. Again, this is history, but I'm not going to test you on it, but I think it's good to know. So U.S. scientists were afraid that Nazi Germany, 1939, World War II, U.S. scientists were afraid that Nazi Germany would develop a bomb based on nuclear fission. And so they persuaded Albert Einstein to write a letter to President Franklin. And this is interesting. Sir, some recent work by E. Fermi and L. Szilard has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable, through the work of Joliot in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by boat and exploded in a port might very well destroy the whole port together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. So that was a letter dated August 2nd, 1939. So what does the government do? Hey, let's build atomic bombs, right? 1941, Manhattan Project, you may have heard of that. That began in Los Alamos, New Mexico, with the goal of building an atomic bomb before the Germans did. And they were successful. First nuclear weapon detonated July 16th, 1945 at a test site in New Mexico. And this is a photograph. I don't know that this is of that particular explosion, but that's what it looked like. You get this mushroom cloud. This had a force equivalent to 18,000 tons of dynamite. A ton is 2,000 pounds. So 36,000 pounds of dynamite, all exploding at once, right? At this point in the war, Germany had already surrendered, but Japan was giving us a lot of trouble. And so 2 bombs were dropped on Japan, killing 200,000 people. It's just mind-boggling, really mind-boggling. Any questions? That's the atomic bomb. If you control a fission reaction, instead of letting it go out of control like that and be explosive, you can use that reaction to generate electricity with no air pollution or greenhouse gases. That sounds really good, doesn't it? It is. It's a really great thing. At the writing of the book, nuclear fission generated about 20% of U.S. electricity and up to 70% of electricity in some countries. So if you have a cylinder of uranium the size of a pencil, that can provide enough energy to power a car for 20 years. It's amazing. A coal-burning power plant uses 2 million kilograms of fuel to generate the same power as 50 kilograms of fuel generates in a nuclear plant. We can get a lot more energy out of a much smaller amount of raw materials. How does nuclear fission as a power source work? Well, the fission generates it releases a lot of electricity, a lot of energy. And so that energy is mostly as heat. So things can get very, very hot. So we use that heat to boil water to make steam. The steam turns the turbine on an electric generator. The basic idea here is not that different from a coal power plant. You use the coal, burn the coal to boil water and turn a turbine that generates electricity. So this is a diagram of a nuclear reactor. So we have, this is all contained in a big heavy-duty containment shell. So we've got the reactor here, and there are fuel rods and control rods. So the fuel rods have uranium-235 enriched fuel in them. And so, making that is another thing in and of itself. And the way they control this is by using neutron-absorbing control rods. So these control rods can be lowered into the reactor, and lifted out. When they get lowered down, the control rods absorb the neutrons that are being generated. And so then they can't go on to induce other fission reactions. You pull them up, and then more fission reactions can be induced. So without the control rods, this would be an atomic bomb. It would just kaboom, and be gone. If you put the control rods down in there and don't pull them out, you stop the whole thing. Okay? So this generates a lot of heat, which is used to create steam, and the steam moves a turbine, which generates electricity. And we don't have any greenhouse gases being emitted, so that's awesome. The drawback, though, is there's a possibility for nuclear accidents, and then we do have waste disposal. It's just much, much less, and it's not being dispersed into the atmosphere. Any questions yet? This is a photograph of an actual nuclear power plant.
Did they use it here in California?
I know that there are nuclear power plants in California. I'm not positive. I don't know for sure if they're actually using them or not. Any other questions? That's something I should really figure out. So, accidents. This is the biggest problem. The fission reaction can overheat, not overheat, despite safety precautions. I believe this is a photograph of Chernobyl. This was an accident that happened in 1986. So this was in, I think it was still the Soviet Union at that time. They were doing an experiment to see if they could reduce maintenance costs on the generator, and it was a disastrous failure. So they disabled safety features so that they could do this experiment. The partly graphite nuclear core overheated and began to burn. There were 31 immediate deaths, and a 32-kilometer radius became uninhabitable. It's still radioactive there. Yeah. So really, really bad deal. Another more recent one, Fukushima, Japan in 2011. There was a tsunami triggered by an earthquake. And what they didn't take into account, because they had all these safeguards, but the tsunami, the big waves from the ocean came in and flooded the ponds where the cooling water was. So the cooling water now had all this debris in it, which clogged up the pumps. So the pumps failed. And so 3 of the nuclear cores overheated, experiencing a partial meltdown. This was not a complete meltdown, like in Chernobyl. But because they lost the water from the fuel ponds, that caused the fuel to overheat. The radiation release here was significant, but it was much lower than Chernobyl, and there were no radioactivity-related deaths reported from this accident. So, I mean, here's another accident, more recent, but the consequences were much less, and so we're getting better, right, at containing these things and preventing accidents. Neither incident was a nuclear detonation. They didn't actually explode because the uranium fuel there is not sufficiently enriched in uranium-235 to actually produce detonation. U.S. nuclear plants have additional safety features designed to prevent such accidents, and so we learn from the mistakes in history. Any questions? The other problem with nuclear power, is the waste. So you do end up with spent nuclear fuel, which is radioactive. The amount of fuel is very small compared to other types of electricity generation, but these products are radioactive and some of them have very long half-lives. So they're not just going to decay anytime soon. So they need to be stored somewhere. You can't just throw them in the river or put them in a landfill. So currently, nuclear waste in the U.S. is just stored on site at the nuclear power plant. They were making a single permanent disposal site in Yucca Mountain, Nevada, but that was stopped in 2010, as far as I know. they have not figured out how to resolve their difficulties, and they're just kind of stuck there. So I think most scientists would agree that nuclear power is a much preferred way of generating electricity compared to coal or other fossil fuel sources. I mean, wind power and solar power are also great, but they do have their limitations as well. The reason that nuclear power has not become more common is basically fear and misunderstanding by the general public. People are afraid of it. And, I mean, you see Chernobyl, and it's like, that was really bad. There was an accident before that here in the United States at 3 Mile Island on the East Coast. Also really bad. But we're learning from those mistakes, and these are not going to go off like a bomb, right? They are not dispersing radioactivity into the atmosphere. It's contained on the site unless there's a serious meltdown.